In this video, we're going to be discussing the properties of rational functions. If you haven't already watched section 5.1, functions, now is a good time to go back and watch that first before we discuss deeper properties. The definition of a rational function is it must have the form of some polynomial divided by another polynomial. And the Q polynomial cannot be 0. The domain is the set of all real numbers except for those which makes the denominator 0. So let's first discuss domain of rational functions. In the first example, part A, we have a function f of x equal to 2 minus x divided by x plus 2. Clearly, the denominator cannot be 0. So x plus 2 can never be 0. If I solve this for x by subtracting 2 from both sides, you're going to find that x cannot be negative 2. So my domain is listed as the set of all x's such that x is not negative 2. But x can be any other real number. So looking at the domain of part B, again, looking at just the denominator, because that's all we really care about as far as exclusions from our domain, we say that x squared minus 9 cannot be 0. Well, if we factor both sides, we get x plus 3, x minus 3 cannot be 0. And using the zero product property, excuse me, you're going to find that x cannot be negative 3 or 3. So set of all real numbers x such that x is not negative 3 or 3. For the next example, we state that x squared plus 1 cannot be 0. This is not factorable. Since it's not factorable, you could try putting this into the quadratic formula. Or we can simply look at it as x is not equal to negative 1. So by just subtracting this 1 over to the other side, you're going to find that x squared is not equal to negative 1. So if I take the square root of both sides, by using the square root property, we find that x cannot be the square root of negative 1. Well, the square root of negative 1 is not a real number. So there are no exclusions, so the domain is all real numbers. It would never matter what x I put in here, I can never get 0 for a denominator. Because anytime I square any number, regardless if it's positive or negative, you're always going to end up with a positive number for x squared. And when you add a positive number and you add one more, you can never get 0. So there are no exclusions from my domain, therefore x can be all real numbers. Looking at this denominator here, we simply state that x squared plus 4x minus 5 cannot be 0. Well, if we factor the left side, we find that x plus 5 and x minus 1 are the factors. So that tells me x can be any number such that x is not negative 5 or 1. So again, recap of domain. You're not finding what x can be, you're finding what x cannot be. So in these functions, x can be any other number in the graph except for these particular values. We're going to use these exclusions from our graph to see what that's going to do in a graphical form. So if we look at another example of graphing 1 over x, this was the reciprocal function back from our library of functions in chapter 3. The reciprocal function, if we remember what the graph looks like, we did discuss this. It is a graph that hugs the y-axis and the x-axis and goes through 1, 1 and negative 1, 1, negative 1. This graph never crosses the x-axis and never crosses the y-axis. Of course, you can make a table of points to verify this, but we already did this back in chapter 3. The domain here, you can see that x can never be 0. Okay, so the domain is the set of all numbers x such that x is not 0. And you can see that on my graph here. X could be negative infinity. It could be any number x leading up to 0, but it never actually gets to 0. It just keeps getting closer and closer and closer to 0, but never actually touches 0. Same thing with the other side. It never actually touches 0. It starts right on the other side of 0, and then x gets closer and closer or away from the y-axis, and then goes to positive infinity. So x can be any negative number, any positive number, but it never touches 0 at the y-axis. So what happens as x keeps getting larger and larger and larger? Well, the function is getting closer to 0. In other words, y is getting closer and closer to 0, or the x-axis. So the function y gets closer to 0. In symbol terms, it says the same thing. As x approaches infinity, which is the same thing as saying as x keeps getting larger, the f of x approaches 0. So this is stating the same sentence as what we stated up here in words. And we would read this as x approaches infinity, f of x approaches 0. So these arrows means approaches or gets closer to. So if we do the same thing in the other direction, as x goes to negative infinity, what is happening to the function? Y is getting closer and closer and closer, again to 0, but from the bottom direction instead of from the top. So as x gets smaller and smaller, the function gets closer to 0. So as x approaches negative infinity, the function f of x, or y, gets closer and closer and closer to 0. So we're going to use this information to discuss asymptotes on the next page. So as x approaches infinity, and as x approaches negative infinity, f of x gets closer to 0. We say that the line y equals 0 is a horizontal asymptote. So looking at this graph right here, back at the graph that we just had, this graph right here, what that is saying is the line y equals 0, which is this line right here, is what we call a horizontal asymptote. A horizontal asymptote is an imaginary line that the graph never ever crosses. It just gets closer and closer and closer to that line, but it never crosses it and goes to the other side. So this line, y equals 0, is a horizontal asymptote of this particular graph. So when the values of the function approach some fixed number, in this case is 0, then the line y equals that number, in this case is 0, is a horizontal asymptote. There also is such thing as vertical asymptotes, which we're going to talk about next. So what happens when we look at the positive values of x that get close to 0? So as x starts to approach 0, what's happening? X is getting closer and closer and closer to 0. The value of y is getting bigger and bigger and bigger. So the value of the function, or y, gets larger. Or in other words, it approaches infinity. So as x approaches 0 from the positive direction, so as it approaches 0 from this direction, so as x approaches 0 from this direction, the value of y approaches infinity. Now what happens when we look at the negative values of x that get close to 0? So from the negative direction, as x gets closer and closer and closer to 0, what's happening to the value of y? It's going down to negative infinity. So f of x gets smaller. So as x approaches 0 from the negative direction, the value of y is really small, or in other words, it's approaching negative infinity. So to put all of this together, as x gets closer to 0, from both the left and the right side, the function f gets larger and larger and larger, both either positively or negatively. Therefore, the graph of this reciprocal function has what's called a vertical asymptote at x equals 0. So on the graph, let's look at that vertical asymptote. Which would be right here. This is a vertical asymptote. It's an imaginary line running through my graph. The graph never crosses through it, and its equation is x equals 0. You can see that this graph gets closer and closer and closer, but never crosses it. So not only do I have a horizontal asymptote, I also have a vertical asymptote. Some graphs can have one and not the other. Some graphs can have multiple of one, multiple of the other, and some graphs can have none. So now let's look at the graph of a function that will never intersect a vertical asymptote. This graph never ever intersects this vertical asymptote. If x approaches negative infinity, so as x approaches negative infinity, goes left, 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 or as it gets bigger, bigger, bigger towards positive infinity, the value of a rational function approaches a linear expression, then the line is an oblique asymptote. So an oblique asymptote excuse me, is not vertical, not horizontal. It's actually a line like y equals mx plus b. And this line could be anywhere in the graph. It could go this way, or it could be this way with a negative slope. So this is what we call an oblique asymptote. This graph actually has another asymptote, a vertical one. This vertical asymptote is right here. Because you can see that this graph goes forever and ever to negative infinity, and it will get closer and closer to this purple oblique asymptote. It also gets closer and closer to this vertical asymptote, but it will never touch it. So this actually has two different types of asymptotes, the oblique asymptote and the vertical asymptote. And by the end of this section, I'll show you how to find exactly where those asymptotes are without the graph. So let's look at this function right here, 1 over x squared, and let's determine where their asymptotes are located. So let's first find what this graph will look like by finding a table of values. So I'm going to plug in some values. Let's start with -2, -1, 0, 1, and 2. And if we need to find more points, we will. So if I plug in -2 in here, we have 1 divided by -2 squared, which is 4, so this becomes 1/4. If I plug in -1, it's 1 over +1. What's 1 divided by 0? Oh, that's undefined there, because the domain does not allow x to be 0. Okay, so that is undefined at 0. If x is 1, again we have 1, and if x is 2, again we have 1/4. So I don't know if this is enough information to graph or not, but let's graph what we have. At -2, positive 1/4, -1, 1, 1, 1, and 2, 1/4. So I'm not so sure that there's enough information yet to graph it. I'm going to graph a couple more points. Let's graph somewhere in between here. Let's graph -1/2 and positive 1/2. If I put in negative 1/2 in here, sometimes it's easier to do this in a calculator if you prefer. So if I put this in my calculator, I have 1 divided by negative 1/2 squared. Which is 4. And I'm going to get 4 for both of those results. So I'm going to have a point at negative 1/2, 4, and positive 1/2, 4. I'm going to do another one at negative 3 and 3. So 1 divided by negative 3 squared is 1/9 and 1/9. So you can see at negative 3, it's at this point just getting closer and closer and closer to that x-axis. It's getting smaller, smaller, smaller numbers. Since I know it cannot be 0, it means it's going to hug the y-axis and go up like that too. So it's very similar to the last graph we had, which was the identity function. If we remember the identity function, which was 1 over x, I had this part of the graph in the first quadrant, but it was symmetric over the origin because it was an odd function. See, the degree of the x is odd, so it was symmetric over the origin. This graph happens to be even. So it's going to have y-axis symmetry. So I still have the piece up in the first quadrant, but since it's symmetric over the y-axis and it's even, the other part of it will be in the second quadrant instead. Okay? Now, we're going to take this information and we're going to use some transformations. First thing I'd like to notice is there are asymptotes in here. There is a vertical asymptote. I can see it running right down through here. This is the vertical asymptote. And the equation of this vertical asymptote is going to be located at x equals 0. There is also a horizontal asymptote. And this horizontal asymptote is located when y is 0. So I have 2 asymptotes. You can see that these graphs will never cross. So now we're going to take this graph and we're going to do some transformations to it on the next page. Okay, so we have this graph. Maybe I'll do it like this. There we go. Okay, so we have this graph and we're going to do some transformations. So in the first graph here, we're actually going to graph just the graph of f of x equals 1 over x squared, because that is what is happening. The x is being squared, so this is what we call the power function. The original power function that we're going to use as our base, and then we'll do our transformations by adding 1 or subtracting 3 within the function to these other ones on the right hand side. So let's go ahead and recreate this graph down here. So we have a graph, and I'm just going to sketch this. We have a point at negative 1, 1 and 1, 1. And then when I put these all together, looks like this. Okay, so now I'm going to take that information and I'm going to transform it. Okay, I know I have, again, my asymptotes. I'm going to my horizontal and my vertical. They're going to shift with the graph. So the first thing I'm going to do is I'm going to shift this graph right 3 units, which means the green line will shift right. Well, when you shift a straight line horizontally right, it doesn't really look like it's moved. If I pick this and move it 3 units, it doesn't really look like it moved. The vertical asymptote, however, if it was on the y-axis and I move it right 3 units, well, now it's going to be located right 3 units over here. So my graph has moved over here. Now I'm going to take that graph, after I shifted it right 3 units, now I'm going to move the whole graph up 1 unit. So now I'm going to move it up 1 unit. So my orange, or my vertical asymptote, moves up 1, which appears like it doesn't move. Then my horizontal asymptote will move up 1 unit. So now my graph is going to be located here. So this would be the final transformation of this function. So how do we find exactly where they're going to be located? If you're given an equation and you want to find exactly where those vertical asymptotes are going to be without actually having to graph it. Well, the first thing you're going to need to do is you need to make sure you put this rational expression in lowest terms, which means factor and reduce. So this means factor and reduce. So what we're going to do is we're going to take this original function and we're going to factor and reduce to find the vertical asymptotes. So this first equation, let's factor. You can see this is the difference of squares in the denominator. So we're going to factor the denominator, and then we reduce. If we can cancel anything with the bottom with anything on top, we would reduce those. But unfortunately we cannot, because I do not have an x plus 1 up top. I do not have an x minus 1 on top. So this is already fully reduced. Once it's fully reduced, decide what makes the denominator 0, because that's where your asymptotes will be located. So what makes this denominator 0? That means I'll have a vertical asymptote at x equals -1 and another one at x equals 1. Remember, we're not stating that x is these numbers. These are the vertical asymptotes, which means there will never be a part of the graph at that particular location. So if we looked at a general little graph of this, I'm going to have a vertical asymptote at -1 and 1, and then my graph will do something in between all of that. The graph will never touch those asymptotes. So I don't know exactly what the graph is going to be doing. I guess I can get an idea by putting it in my graphing calculator just to get a visual of that. So if we want to get a visual of what this will look like, we do x divided by x squared minus 1. And here's the graph. So the full graph of this is going to be something that looks like this. So you can see that that graph never crosses those vertical asymptotes. And those vertical asymptotes are located, again, at -1 and at +1. And the green graph never crosses through that anywhere on the graph. So let's try another one. Again, we have the same denominator, so let's go ahead and factor this one. So we have x minus 1 over x plus 1, x minus 1, but this time we actually can reduce. You're going to see this, these x minus 1s will actually reduce. So once it's fully reduced, it's equal to 1 over x plus 1. So I actually only have, this time, one vertical asymptote. The only place I'm going to have a vertical asymptote is going to be located at x equals -1. So in a graph over here, the graph of this is only going to have one vertical asymptote at -1. So there will not be another one on the other side. So if we look at what this one would look like, we have x minus 1. I should put that in parentheses. X minus 1 divided by x squared minus 1. And we graph that, you'll see that there's only one asymptote. So the graph does the same thing on the left side as it did up here, but up here it looks like that. There's not that second asymptote because we were able to reduce this and cancel out the other asymptote. Finally, the last one, again, if we go ahead and we factor this, oh, wait a minute, the sum of two squares, hey, that's not factorable. There's nothing to reduce. This is already fully reduced. It's not factorable. What x makes this 0? Nothing. There are no x's that will ever make this denominator 0. Remember, we have a positive plus 1, which can never be 0. Since there are no exclusions from my domain, there are no numbers that will ever make this 0. That means they're all real numbers are possible, which means there are no vertical asymptotes. So if we look at a graph of that, we have x divided by x squared plus 1. So it kind of just does this little blip in the middle. Let me try to zoom in a little bit there. So you can see it just kind of does this little movement in the middle. So if I wanted to graph this, I'll do it a little bit bigger. It looks something like that. So there are no asymptotes. Okay, so finding your asymptotes tells you a lot about the graph, at least so you know what it's getting closer to around the asymptotes itself. So that was the vertical asymptotes. Now we're going to find the horizontal or oblique asymptotes. Remember, the horizontal ones go sideways and the obliques are diagonals. So now in order to find the horizontal or the oblique asymptotes, we look at the power of the top and the bottom. Okay, so the power of the top is n, the power of the bottom is m, and we compare the degree of both of those. You always look at the highest order of each of the first terms. If the degree of the numerator is smaller than the denominator, this is what we call a proper function, like a proper fraction. A proper fraction has a smaller number on top than it does on bottom. If it is proper, then you automatically have a horizontal asymptote at y equals 0. So a graph of that, a horizontal asymptote at y equals 0 would be right here. So it would have a horizontal asymptote on top of the x-axis. If n is equal to m, in other words, the same degree on top and bottom, they match, then you will have a horizontal asymptote at the line y equals whatever the division of these two numbers are. So for example, if a is 4 and b is 2, 4 divided by 2 is 2. So you'll have a horizontal asymptote at y equals 2, which would look like this. So your horizontal asymptote will move based on what the coefficients are in front of those first two terms. Then the oblique, the third option says, well, what if the degree of the numerator is larger than the denominator? That means you have an improper fraction. Then we have what's called an oblique, and we use what's called long division. So if the degree of the numerator is 1 more than the degree of the denominator, the quotient of the division is where we find the oblique asymptote. If the degree of the numerator is 2 more than the degree of the denominator, then the quotient obtained is a polynomial of degree 2 or higher, and R does not have a horizontal, nor does it have an oblique. So we're going to do examples of all 4 types. Numerator bigger than denominator, numerator smaller than denominator, numerator equal to denominator, numerator bigger than denominator by 1, and then numerator bigger than denominator by more than 1. So we'll do an example of all 4 types coming up. So here we've got some examples to finish out this section, and we're going to determine what type of asymptotes they have.